we want to give a cohomological description of the Brauer group. To motivate this cohomological approach, we want to start with the classical viewpoint. This is actually Brauer's original approach in studying central simple algebra. To each equivalence class of central simple algebra in the Brauer group, Brauer associated something called the corresponding factor set. It turns out that it gives a bijection between elements of the Brauer group and the equivalence classes of factor sets. So what are these factor sets and what is this map here? Alright, so note that any element of this Brauer group here has a unique representative that contains K as a maximal subfield and has degree equal to n squared, where n is the dimension of big K over little k. Given such a representative S, i.e. a central simple K algebra of dimension n squared, containing K as a maximal subfield, we're gonna construct a factor set as follows. Observe that by Skolem Noether, every element of the Galois group of big K over little k is a restriction of some inner automorphism of S. That is, if we let phi be the map associating to every element little s in S the conjugation by S map restricted to K, then this is surjective onto the Galois group of big K over little k. Note that the kernel of this map contains all the element little s that commutes with element of K, i.e. the kernel of this map must be the centralizer in S of K, which must be K because K is a maximal subfield. That is just by our definition of maximal subfield. It's the subfield of S whose centralizer is equal to itself. So in other words, we see that conjugation by S and conjugation by T restrict to the same map on K if and only if T inverse S lies in K. That is, if and only if T and S differ by a scalar in K. In other words, the fiber over any element sigma of the Galois group just consists of scalar multiple of some element S. So now let us choose for each sigma an element S sigma in this fiber. That is, conjugation by S sigma is gonna be equal to sigma on K. Then observe that S sigma times S tau and S sigma tau lie in the same fiber under phi because they both map to sigma tau. That is because for every element little a in big K, conjugation by S tau applied to A should be equal to tau A. And then conjugation of that by S sigma should be equal to sigma of tau A. So A conjugated by S sigma S tau should be the same as sigma tau A, but that's just the same as A conjugated by S sigma tau by definition of S sigma tau. Thus, S sigma S tau and S sigma tau lie in the same fiber over phi, so by our previous discussion, they must be scalar multiple of each other. That is, there must exist some scalar A sigma tau inside K, such that S sigma S tau is going to be equal to A sigma tau multiplied with S sigma tau. And we call this A sigma tau, S sigma and tau range over G, we call this a factor set relative to big K. We should view this factor set as a map A from G times G to K, associating to each pair sigma tau the element A sigma tau inside K. Now, of course, this factor set is not unique. Well, the factor set is uniquely determined by this section S, but this section S is not uniquely determined by this central simple K algebra S. So let's see what happens if we choose another section. So let T be another section of the map phi. That is, for every sigma, we want T sigma to be an element in the fiber over sigma. That is, conjugation by T sigma should be equal to sigma on K. Now let B be its corresponding factor set. So that means that we have a similar relation here. We replace S by T and A by B. Then observe that since T sigma and S sigma lie in the same fiber of V, namely they both lie in the fiber over sigma, by our previous discussion, they must differ by a scalar in K. In other words, there must exist some scalar F sigma in big K, such that T sigma is equal to F sigma times S sigma. Thus now we have two ways of computing T sigma T tau. One way is via this identity. We replace T sigma with F sigma S sigma, and then T tau with F tau S sigma. And another way is to use the definition of factor set. We know that T sigma T tau and T sigma tau lie in the same fiber over sigma tau, so they are scalar multiple of each other, and by definition, T sigma T tau is just B sigma tau multiplied with this T sigma tau. Now we want to relate this factor set B sigma tau to this factor set A sigma tau. So we want to make this A sigma tau appear here, and for that we need to have S sigma S tau next to each other. Thus we just perform a little trick and insert in here a factor S sigma inverse S sigma. So then this S sigma S tau becomes A sigma tau times S sigma tau. So we got this factor set. On the other hand, S sigma F tau S sigma inverse. What is this? Well, this is just F tau conjugated by S sigma, but F tau is an element of K, and we have said that conjugation by S sigma on K is just the same as applying sigma. That is the definition of S sigma. So then we can replace this whole pink term with sigma of F tau. Thus, here we have a relation relating these factor set B sigma tau and A sigma tau. So we say two factor set A and B are equivalent if there exists a collection F sigma in K such that this whole. Thus, to each central simple K algebra having K as a maximal subfield, we have associated an equivalence class of factor sets. Thus, we have a well-defined map from the Brauer group of this big K over little k to the set of equivalence classes of factor sets. In the next video, we're gonna show that this map is actually surjective and thus an isomorphism. But to do so, we wanna first give an intrinsic definition of factor sets that do not really refer to this external central simple algebra S. And this would motivate the definition of cocycles. We'll do all of that in the next video.